Okay, welcome back now to our class. Now, today we will be discussing the Laplace transform of periodic functions. But before we start our discussion, we need to know what are these periodic functions. Let's start with some examples of periodic functions. Let's say I have here some periodic functions. Okay, these are examples of periodic functions. Let's start with the very common periodic function. We will call this function as a square wave. So a square wave function, okay, this is a square wave function. This is also a periodic function. Okay. So this is common in your electronics subject, the square wave function. Okay, let's label this as time and your y-axis as your function of t. Now, if this is your amplitude a and this is negative a, we call this function as square wave function. Mathematically, it is defined as, so this is the mathematical definition of this function. The value of f of t is equal to a when, okay, assuming that we will put also the values of time here. Let's say I have here pi, 2 pi, 4 pi, and so on. Right, now going back from 0, between 0 and pi, okay, the value will become positive a, and it becomes negative between pi to 2 pi. So this is how you represent the first period of the function. So we will label the period here. So this is the period of the function, one period. So period is defined as t. So t is actually the time where the graph now completes one cycle. So we call this one period. That is why it is called periodic, because it repeats, it keeps on repeating the cycle. So that is why it is called a periodic function. Okay, meaning to say, everywhere, on anywhere, not everywhere, anywhere on the graph, with a period of t, you will have the same value. Like for example, this will be, okay, this is an example. Okay, this is an example of one period. This is also the same as the period here. Same as the period here. So meaning to say, if you want to measure from this point up to this point, they will have the same value for a period of t. So that's how periodic function works. Now, mathematically, it is defined using this function, but you need to add that the function of t plus the period of 2 pi will be equal to the function of t. So meaning to say, this function defines your periodic function. So do not forget this one, because this function illustrates that the function there is a periodic function. Okay. This is a square wave function. Let's try another type of function. Okay. Let's try a rectangular wave. So I will draw a rectangular wave here. Forgive my sketch. Okay, now this is a rectangular waveform. Let's say function is from that point to that point to this point, and another function, okay, another part of the waveform. But this is how periodic function is defined. Okay, that's it. The graph will continue until t equals to infinite value. Now, as you can see here, now let's label it first. Let's label the amplitude. Let's see, the amplitude is, let's say, 2a. This is a, and this is 0. The time here is 0, and we have here 2, we have here 3, we have here 5, 6, 8, and so on. Okay. By inspection, you can solve the period to be equal to 3. Okay, so by inspection, it is known that the period is equal to 3 because you have here one complete cycle. Okay, it's one complete cycle. So meaning the period is equivalent to 3. Now, mathematically, you can represent the function, let's say function of t. Function of t is equal to the value of 2a from time between 0 and 2. And the value becomes negative a. So this is negative a. So the value becomes negative a between 2 and 3. And don't forget that the function of t plus the period of 3 is equals to the function of 3. This is how you define your periodic function. Mathematically, this is your periodic functions in letter B. Okay, now let's try another function. Letter C. Okay, now I will create another function. This time, this is a sinusoidal function. So this is a sinusoidal function. Let me draw the sinusoidal function first. Okay. These are the amplitude of the sinusoidal function. I hope I'm doing right. Right. Okay. And then I will trace the function here. This is my sinusoidal function. The sinusoidal function is actually a function of sine or cosine. So that's how you define a sinusoidal function. Okay, assuming that is my function. I'm not good in sketching, but as you can see here, this is a sinusoidal function. So let's label it as t, and this will be your function of t. So in this case, your function of t is defined by a sine omega t. Okay. So we will have the amplitude here as a, and here is your negative a. So your omega, we all know that f, okay, omega is equal to 2 pi of f, right? And f is equal to 1 over t. Okay. Now, if you want to know the period of this function, the period now is from 0 up to that point. Okay. Let's label this as t. Let's say this is 0. This is your t. That's your omega. So, like for example, if it is given, let's say instead of omega, I will be changing this value. Let's change this value to t only. Sine of omega t. Sine of omega t, meaning omega is equal to 1. So in this case, omega is equal to 1. You can change that to 1. So you go 1, and then your period, erase this part first. Your frequency is now equal to 1 over 2 pi. This is now your frequency equals to 1 over 2 pi. Therefore, the period is equal to 2 pi. So meaning to say, now if this is sine of t, we can label this as 2 pi for the period. This is pi. So meaning to say, t is your period. So how do we define this mathematically? So mathematically, it can be written as function of t equals to a, that's the amplitude sine of t. This is the mathematical definition for your sinusoidal function. The same is true with your cosine function. Okay, now we will go to the next function, the next topic, which is the Laplace transform of the periodic function. Let's have an example here. So this is my example. We are going to find out the Laplace transform of the periodic function. So here is our example number 1. We are going to plot the function and solve for the Laplace transform of that function. Let's say f of x. Let's say the function is given. Function of t is equal to, let's say this is 5 from 0 up to 5, 0, okay, from 5 up to 10. And of course, your function of t is a periodic function. This is function of t plus the period. So obviously the period is 10 equals to function of t. So this is now the given. Okay. First thing to do is to plot the function first. According to the problem, you have to plot the function, then solve for the function of x. Okay. So we can actually we can actually solve the function here. Solve the Laplace transform the function. But no, in our case, now for the sake of discussion, we need to plot this function. So the solution will start by plotting the function. This is my x and y axis, f of t versus t axis. Okay, now let's plot the function. From 0 to 5, let's label this. This is 0, and this is 5, this is 10, this is 15, and 20. From 0 to 5, the value is 5. Assuming this is 5. That's 5. The value is 5 from 0 to 5. And then from 5 to 10, the value is 0. This is 0. Since this is a periodic function, the function will just repeat itself. This is now your periodic function. Start first. Okay. Now, as you can see there, now the amplitude is 5. Now between 0 and 5, and then between 5 and 10, the value is 0. Now we need to define our period. So by inspection, we can say that the period is equal to 10. We can also see that period in the function itself. Given the period is equal to 10. Now here comes the good part of the topic is to take the Laplace transform of the given function. So by definition, this is the definition. Now if f of t is periodic, then the Laplace transform, let's say, then the Laplace transform of the function of t is equal to 1 all over 1 minus e raised to minus s of t. So here t is your period multiplied by the integral from 0 to t of your function of t e raised to minus st dt. This is the definition of your function. of the Laplace transform of your function of t. And take note, t here is your period. So in this case, this is your period t. Okay. Now let's take the Laplace transform. Now, as we all know that the period is equivalent to 10, so we can just say this is 1 all over 1 minus e raised to minus 10 s, because t is equals to integral. Oh, since from 0 to 10 we have two values of amplitude, we can just say from 0 to 5, this is multiplication. From 0 to 5, the value is of ft is 5 multiplied by e raised to minus st, okay, multiplied by t, plus from 0 to 10, not 0, no, from 5 to 10, okay, the amplitude is 0 minus times e raised to minus st dt. This is how you represent your integral. So the next thing that you should do after this is to what? Next thing that we will do is to take the integral. Okay? So if we will solve for the integral, okay, take note, this is just 0. This is just 0. And the integral of this function is 2 all over s, which is negative, multiplied by e raised to minus. By the way, this is not 2, that is 5. So we can rewrite this as negative 5. Okay. Multiplied by e raised to minus st with limits from 0 to 5. That's the limit. Now simplifying it further, we will have 1 all over. Okay, now let's take out negative 5. Let's take out negative 5. And s 1 minus e raised to minus 10s. And then we will substitute the limits here. Upper limit, which is negative 5s, minus lower limit, which is e raised to 0, that becomes 1. So if you will notice that this term and this term now have a common factor. Now if we will put the negative back to the factored form, so we will have a 5. I will put back the negative. This will become 1 minus e minus 5s. And then I will factor out the denominator here. So since the denominator is actually the square or the difference of two square, we can say this is 1 minus e minus 5s all over 1 plus e minus 5s. This is the factor of your denominator. You can cancel this so leaving you the value. So then it will give you the value of 5 all over s all over 1 plus e raised to minus 5s. This is now your function of s, or this is the Laplace transform of your periodic function. Okay. So this will be now your final answer. That's how you take the Laplace transform of the periodic function. So another method, I will show you another method. This is a simple method that I actually use in some of my classes. Okay. This method is the same method. Now let me draw first the graph. So this is your alternate solution. So in your alternate solution, let me redraw the graph first. Okay, this is your t, this is your function of t. This will be your plot. So let's make the plot simpler. Oh no, this is not that since it should end with 0. Right. So again, this is one. This is now the plot of the function. So this is 5. This is 0. This is 5, 10, 15, 20, and now, a while ago we know that the period is equals to the value of 10. So that's the period. Now, what we will do here is just take out one period. This is one period. This is one period. So we are going to take that out and represent that period as the function of the unit step function. So we will represent this period as a function of the unit step function. So this is function of t is now equal to 5 multiplied by the window function u sub t minus u sub t minus 5. This is now the representation of the period function of one period. Since this is 0, we don't have to write it. So this is now the representation of your function of t for one period. Now, what are we going to do here is to solve for the Laplace transform. Let me change the color here. Solve for the value of the Laplace transform of the function t. We are going to solve the Laplace transform of one period only, divided that by 1 minus t minus st. So we need to take the Laplace transform of one period. Take note, this is just your function of t here is the one period function. So we can have this as 5 u sub t minus 5 u sub t minus 5. Or we can just say, let's just factor out 5. Let's factor out 5. Let's put it here. And then you have the Laplace transform of u sub t minus the Laplace transform of u sub t minus 5. Okay, this is your one period Laplace transform. All over 1 minus e raised to minus 10. Since we know that t is equal to 10. So simplifying the numerator, we will have 5 multiplied by 1 over s, right? Minus, we have to e raised to minus 5s, since that is shifted by 5 units, all over the denominator 1 minus e minus 10 of s. Now, if we will simplify it further by factoring out s, we can have 5 over s, and what's left in your numerator is 1 over 5s. And then take note, we can factor also the denominator, since the denominator is the difference of two squares. So we can have this as 1 minus e raised to minus 5s. Okay. Zoom. Okay. 1 plus e minus 5s. Now we can eliminate the common factors. And what will remain here is 5 all over. It's multiplied by 1 plus e minus 5s. All right. Now, this is your function of s. The next thing that we will do here is to solve for this problem. So now you already understand how Laplace transform works in a periodic function. Now it's your time to solve this problem. So solve this for, let's say, 20 minutes. It will take note, this is your practice problem. So you have to solve this for 20 minutes. So I will give you the function here. Okay, this is a periodic function. Let me label it first. Okay. This is from 0 to 1. This is from the previous example. I want you to find the Laplace transform of this periodic function. So if you can still recall, the first thing that you should do is to first find the period. Okay, assuming the period here is 0, here at the time, okay, 0, let's say 2, 4, 6, 8, 10, 12, 14, 16. Okay, now for 20 minutes, solve for the Laplace transform of the function of what is the Laplace transform of the function. Try to solve this, and then I will not give you the right answer. Okay, all you have to do is to solve this and then PM me your answer. Okay, that's it for today. I will stop this recording